The precision of artillery fire has always been a problem that military designers need to solve. Now with the advancement of science and technology, improving the accuracy of artillery requires considering the processing precision of the gun barrel and ammunition, as well as guided ammunition technology. However, 200 years ago, the precision of artillery fire was still plagued by the firing structure. Like early firearms and matchlock guns, the firing structure of early artillery was relatively primitive. Due to the large amount of gunpowder used in artillery, incidents of injury caused by the flame shooting out from the touch hole were not uncommon. For a long time, the method of artillery fire was to ignite the matchlock, and the burning matchlock would ignite the gunpowder at the bottom to complete the firing process. This structure was relatively simple, and the shooter had a certain amount of time to leave the artillery when igniting the matchlock to avoid being injured by the high-temperature exhaust gas leaked during firing and the violent recoil of the gun carriage. However, this structure also had many problems. First, the matchlock itself was prone to moisture, and daily storage and rainy weather during combat would affect the success rate of firing. It would also affect the burning speed of the matchlock. Therefore, if the matchlock was ignited but the firing was not successful, the shooter could not immediately check because it might just be that the burning speed had slowed down. In addition to the success rate of firing, it also had a significant impact on accuracy. If it was a static-to-static fire, then a longer burning time for the matchlock would not matter. But in naval combat, it was a different story. Before the widespread use of rotating gun turrets, artillery could only be placed on the sides of warships. Although the firing angle could be adjusted manually by manpower, it was very inconvenient. Therefore, how to accurately operate the warship to align the side of the ship with the target for firing was a technically challenging task. Because enemy ships were also constantly maneuvering, seizing the fleeting opportunity for an accurate shot was very important. This was precisely the weakness of the matchlock firing structure. The burning of the matchlock required time, and a longer matchlock could delay the opportunity for firing, while a shorter matchlock could accidentally injure personnel. In the early 19th century, designers finally found a new way to solve this problem, which was the flintlock firing structure. The flintlock gun appeared in the mid-16th century and was gradually popularized in the West around the 17th century after continuous improvement. The benefits of the flintlock structure were numerous, with the most important being timely firing. After pulling the trigger, the related structures would start moving, and the flint would strike the iron anvil to produce sparks, which would then ignite the gunpowder. By the 18th century, most Western armies were equipped with flintlock guns. However, it wasn't until the early 19th century that designers successfully designed flintlock firing structures for artillery. This was related to the advancement of metal processing technology at the time, as it was much more difficult to install flintlock mechanisms on heavy artillery and still maintain their structural integrity compared to rifles. Britain was the first to implement the flintlock structure on their rear-loaded artillery. The basic principle was the same as the flintlock rifle. Its appearance increased the efficiency of artillery fire. The shooter completed instantaneous firing by pulling the rope, combined with the accuracy and range advantages of rear-loaded artillery. It instantly became one of the cutting-edge technologies at that time and was one of the technological equipment that the Royal Navy used to maintain its maritime superiority. When it came to specific operations, after the loader completed loading the ammunition, the gunner would observe and adjust the firing angle of the artillery through a simple mechanical aiming structure, then quickly move to the right side of the artillery. The shooter on the left side would quickly pull the rope to engage the flintlock structure. While performing this step, the shooter would not bend over, but stand straight and extend their arm to avoid being injured by the high-temperature barrel during continuous firing. After attaching the rope, the gunner would order the firing, and the shooter would quickly pull the rope, causing the loop to disengage from the flintlock structure. The shooter would then prepare for the next shot by winding up the rope. The whole process was swift and decisive. Compared to front-loaded artillery, the rate of fire was significantly increased, with some small-caliber field cannons being able to fire in less than a minute, which was considered a remarkable technological advancement at that time. During the Opium Wars, the British Navy's rear-loaded artillery mainly used the flintlock structure for firing. In contrast, the artillery used by the Qing army was not only mostly old equipment, but the newly cast artillery also had old-fashioned structures. There was a clear gap between the two. It was indeed surprising that they were able to win battles under such circumstances.